So welcome back. In the last lecture that we started, we got to look at what binary phase diagrams and what they look like and how they really are. They can be navigated either using tie lines and the lever rule to tell us what the compositions were in two phase regions and then how much of each of those phases were there. We're going to take a little step further now and start looking at what I consider to be common phase transformations. Whereas not every phase diagram that we look at is going to be an isomorphous solid solution. And like the nickel copper system that we were looking at, where there are other features to these phase diagrams that we can look at that tell us a lot about how different materials interact, particularly in the solid state or going from different phases, whether it's liquid to different solids or solids to solids or anything like that. So we're going to talk a little more about these, but before we get there, quotes of the day. Sir Henry Royce, you can imagine what he did, mostly with Rolls-Royce Company. And I do like this as a way to think about things is, take the best and make it better. Definitely something that you could imagine in the aircraft engine business that would be very useful. And then they'll, of course, be complete without a quote from Homer Simpson. And we're going to see that thermodynamics is really important in what we're talking about as we move forward. So what are we going to really talk about in this lecture? And what it is a closer examination of phase diagrams. And we're going to concentrate in these binary systems on what we call invariant transformations, or transformations that occur at specific temperatures and compositions. And so they're invariant. They can only occur under these conditions. They have really no degrees of freedom that allows them. And eutectics are one of the more important of these types of transformations and systems. And what these are is the ability to take a liquid directly to two solids at one temperature. Whereas we had talked about that alloy systems and most compositions have a melting range, where there's a range where you have liquid and solid coexisting. Not so in the eutectic system. These systems go directly from a liquid to two solids. And so for casting and soldering and a lot of these industrial processes where solidification and a tight control of solidification temperature is important, these are important transformations. We'll see how they appear on phase diagrams. And then looking at the development of microstructures in these eutectic alloys. And we're going to see if there's a lot we can do to play with them by playing with composition and working our way along the composition system, and how many different alloys and different types of alloy systems can come out of just playing or at least manipulating the composition around an invariant transformation like a eutectic. We're going to see also, when we talk about intermediate phases, that most alloys do not have just a single solid phase. They have multiple solid phases, and these solid phases can exist away from the extremes of the phase diagram, where we would have nearly pure one element or component or pure another element or component. So these intermediate solid state phases are going to become rather complicated, but they can also become very important. And then there are other types of invariant transformations that we're going to talk about, and eutectoid and the paratectic are two of the more important of the two. The eutectoid is probably the most important of these. And we'll work our way down into the Gibbs phase rule, which is really the basis for the phases that exist within a phase diagram. And so readings from Callister, similar to before, and as always, your practice problems, the one with the asterisks, are part of your homework assignment for this lesson. But as always, I highly recommend that you take care and work through the other problems that are listed here. And I will post the solutions at the end of the lesson on Canvas. So what's our important terminology? We're going to see that there's a little bit more here than we had before. Solvus, we had seen solidus and liquidus before, but the solvus is basically a boundary between two solid solutions or two solid phases in the binary phase diagram. The eutectic we briefly talked about. Microconstituent is what the product of a eutectic or eutectoid transformation may look like. And so it's a combination of different phases. Intermetallic is something we're going to get into, and a lot of these other ones we're going to run through. So keep an eye on as we work through these important terms, and you'll be seeing them again on the next exam. So what does a eutectic system look like? Now, if we go from our nickel copper system and take a close look at that, what we had was just a single region of liquid plus solid across the entire compositional region that we were interested in. So in this case, we see something a little more complex. We see at the edges in this type of system that we have a single phase, which is really close to the pure component, in this case copper, in this case silver. And so the other thing we tend to see here is they can blend. So across the range of compositions near as we approach room temperature, we actually have more than one type of solid phase, which means they have different crystallographic structures to them. So these phases are homogeneous in and among themselves, but they can be mixed together into a more complex microstructure. Now, when we look at these types of phase diagrams, and this is always a cue that I always look for when I'm presented with a phase diagram that I may not be familiar with, is a horizontal line. So a horizontal line tells me that I'm going to have somewhere along there an invariant point, because what it's telling me is that at that temperature, nothing is changing at this single temperature. So horizontal is a key that there's something that is different about this. And in this case, what we see is a eutectic type of transformation. We're going to identify some other transformations as we move forward, but at this eutectic point, at this very specific composition, which fortunately in most cases on phase diagrams, people will write down the temperature at which that invariant occurs and the composition. So in this case, at about 71.9 weight percent silver in this alloy, and at about 779 degrees C, we have a point where we can go directly from the liquid on cooling, we go directly from a liquid to alpha plus beta, or these two solids. And so I always think of a eutectic of this way, is it's a liquid to two solids at a specific composition and temperature. And so with that, we also have some other lines that we might want to take a look at. We have the liquidus. We have a solidus, which we had reviewed before. The liquidus, in this case, on cooling at a specific composition, would be the point where we first see solid form. And then the solidus on cooling would be the last place that we see liquid, where we have this type of transformation. Now, the solvus, as I mentioned, is a boundary between solid phases. So the solvus here, and there's a solvus on this end. So solvus refers to solid. If I were you, I would write that down as we keep moving forward. So if we really start taking a little closer look at this, well, if we go to the liquidus and we drop in temperature, we see, just drawing tie lines, imaginary tie lines across there, if we follow the liquidus, we see how the composition of the liquid is becoming richer and richer in silver as we drop in temperatures, if we start with this 30 weight percent silver alloy. So the solid sort of really maintains as we drop through, changes a little bit, but that liquidus is changing at this rate. And so as we form more solid, the liquid becomes richer in silver until it reaches this eutectic point. At this point, the composition of the liquid matches the eutectic. So if we were to go just to 778.999 degrees C at this point, we would have whatever solid we formed here, this alpha phase, and then at this point, all of the liquid that's remaining transforms directly to alpha plus beta. We're going to see that that has a very unique microstructure to it. So let's go to another very common eutectic system and work our way through it. It looks really similar to the copper-silver system, but lead-tin was very commonly used. Certain government organizations have real issues with lead and alloys made from lead, so they're not really widely used. In some cases, they're illegal to use. They're tightly controlled. There are issues, as you can imagine, with lead exposure, especially in drinking water and other places. So if we look, though, at this, with the lead-tin alloy, we see a really low melting temperature for the lead as well as the tin. And what this made lead-tin very useful for was solder. And so if you were soldering electronics or doing different things, building your own types of home kits for electronics, when I was younger, you could almost build your own computers, and that was really something to look at, or radio sets. But Today, it's not as common to see a lot of people soldering, but solder with lead tin is common. So if we take a look at this, we want to look at what are the mass fractions, the alpha and beta phases in a 40 tin 60 lead alloy at a temperature 150 degrees C. So if you get a question like that, the first thing you do is you go to your phase diagram and you say, okay, I want 40 tin. So I look here, composition of tin in weight percent goes here. So that's my composition. I'm going to go to 150 degrees C. So I put a point there. Then I look at where I am. I'm in a two-phase region. I'm in this alpha plus beta region. So the next thing I do is I draw a tie line across the compositions. And so I hit these two solvus lines, and then I drop my verticals. And what this tells me right off the bat is what is the composition of my alpha phase, what is the composition of my beta phase. And we see the alpha is going to be really rich in lead, the beta is going to be really rich in tin. And so at this temperature, so how much of each do I have? So if I want to know the mass fractions, I'm going to use the lever rule. And right down here, what we see is that the alpha phase only has 10 weight percent tin. The beta phase has 98% tin. And so from that, if I want to figure out how much alpha is, I go to the opposite. So I take the length of this line. So 98 minus 40 over the entire length, 98 minus 10, that gives me about 66% alpha at this point. And looking at it, it makes sense. I'm closer to the alpha region at this composition, so I should have more alpha at the end of the transformation, or at least at this temperature. But if we look at what happened before, say if I were to cool it down through here, I've gone through a eutectic system. So we're going to get into what happens as we cool down. That's where microstructural development in eutectic systems really starts. But back to the lever rule, we can figure out the beta phase by going to the opposite. So the 40 minus 10 over 98 minus 10 gives us 34% of the beta phase. So add them together, we end up with 100%. Pretty good venture that we're right here. We passed the vision test of looking at where that composition is with relation to the phases in the phase diagram. And using the lever rule, we see we end up with about that much. So it's a little more complex though in a eutectic, isn't it? So, and then what I can do here as well is, because lead and tin have significantly different compositions, we see that these shift a little bit. We go from the 66-34 into the volume fractions of 57-43. And what that has to do is really with these densities. So we can do the same thing that we had talked about in the previous lecture of converting mass fractions, which we read on the phase diagram, to the volume fractions, which we may look at in a micrograph. But in this case, it's mostly because of this significant density difference. That is not always the case when we look at most binary alloys.